Okay, we know the volume of a right circular cone of radius x and height y is given by this formula, v equals 1/3 pi times x squared times y. And we are supposed to suppose that the volume of this cone is going to be 21 pi cubic centimeters. So this is a value of our volume that's given here. And our goal on this is we eventually want to find dy dx when x is 3 and y is 7. Well, we could rearrange this, get y on one side all by itself, but what I'm going to suggest is we go ahead and we're going to use implicit differentiation to help us. So the first thing I'm going to do is I'm going to replace v with 21 over on the left-hand side. And then on the right-hand side, I'm just copying this down for right now. And I'm not replacing in x equals 3 and y equals 7 at this point because we want to find the derivative first and then we'll plug those in. So how I'm going to visualize this with our implicit differentiation is basically 1/3 pi is a constant, so I'm going to leave that alone and it's going to carry along to the next step. And I'm going to worry about what I've put in brackets and really plan out how we're going to take the derivative of this. Well, we have two different functions with two different variables, and they're being multiplied together, so I'm going to visualize this as f multiplied by g. All right, and write out our formula to go along with this. So our formula is going to involve the product rule. All right, product meaning multiplied together, and that is going to work out to be f prime times g plus f times g prime. A lot of times writing out what formula you're using makes life easier as you get working with it. All right, so first off on the left-hand side, we have 21, which is a constant, so its derivative is just going to be 0. Now, we said we were going to bring along this constant, the 1/3 pi, from out in front, and then focus on just what's on the inside taking that derivative. Okay, so first off, the derivative of f. Okay, so we're visualizing x squared. We're going to use the power rule, bring the exponent down, reduce the exponent by 1. So that'll be x raised to the first power going along with that. Now our variable was x. We could put a dx here, but we tend not to do that because dx over dx makes 1. Next, we want to copy down. This is going to be multiplied by our g function, which in our case is y. Plus, now we copy down the x squared function, multiplied by the derivative of our g function, which is just y, so the derivative there is going to be a 1, but with that, we go dy dx. Because our variable is y, we're taking the derivative of that with respect to x. All right, from here, it's a bit of rearranging, isolating that dy dx on one side by itself. In fact, what we could do if we wanted to, we could either distribute that 1/3 pi to each one of these terms, and that would be perfectly fine, or we could divide both sides by 1/3 pi. The purpose being, it's multiplied by the entire right-hand side. We can eliminate it by dividing, kind of counteracting that multiplication, getting the same thing numerator and denominator, therefore getting a 1 multiplied out in front. Now what that's going to leave us with on the left-hand side is 0 divided by some number is going to be 0. But we still have our 2xy plus x squared dy dx. Simply bring along what was inside those brackets. To isolate the dy dx, hopefully not going to be too bad, we're going to have to move that 2xy term to the other side. Now we subtract it because we had a positive 2xy. Subtracting 2xy's makes 0xy's over on the right-hand side. On the left-hand side, now we'll get 0 minus 2xy. On the right-hand side, we're still left with x squared dy dx. And still needing to isolate that dy dx, we need to eliminate the x squared. Well, it's connected with multiplication at this point, so we can divide both sides by x squared. The multiplying and dividing, or getting x squared over x squared, creates a 1, and this will isolate our dy dx. So we get the dy dx on the right-hand side by itself. Now the left-hand side, we can do a little bit of simplifying here if we want to. Because everything's connected with multiplication in the numerator, we have one factor of x can eliminate one of these copies of x from the denominator. So what remains is going to be negative 2y over x. So we're almost done. We've isolated the dy dx. We have our derivative with respect to x on this function. But remember, we haven't used these values up here yet. X equals 3, y equals 7. So let's input those into our derivative function that we found. So x equals 3, y equals 7. To finish this up, this is going to be x equals 3, y equals 7, gets plugged in. A little bit of simplifying down here. We'll go ahead and say negative 2 times 7 is negative 14 over that 3. All right, so when we get done, that's our final answer. That's our derivative of this volume function, the derivative of y with respect to x. So I hope this helps out as you're working on partial derivatives. Good luck. Take your time. You can do this.